Co-17A in the morning. Today is the 15th. 15th. Oh, by the way, I meant to say this last week and totally forgot. We will not be having class on Thursday. I will not be there. So yeah. So I don't know what my plan is yet for Thursday, but I would say my plan is probably to realistically to find a video that I think is in the right, that I've recorded before, that I think is in the right place for you. So probably a video more on continuity and maybe the limit definition of the derivative, because those are probably the next couple things you're going to be doing in class. So I will scour my old videos to find something that I think is a good match. I wish I had the time to make a new video, but I really don't think I do. So that's probably the plan. So yeah, I'll also post an announcement that we will not be meeting for class on Thursday. It is also probable that we will not be meeting for class on the following Tuesday, which I feel bad about, but there's a doctor's appointment that I cannot avoid. So I'll post announcements about that as well. So that's the plan for Thursday. We'll see what the plan is for Tuesday, unless I can move things around. Yeah, so yes. All right, moving on with the math. So let's talk about some recursive sequences. And I know we did like one example of a recursive sequence. I don't think it was last class. I think it was the class before last class. Again, those are the ones that are defined in terms of like the previous term. In fact, a very famous recursive sequence is the Fibonacci sequence. The Fibonacci sequence, just to give you a kind of neat example, is defined this way. F sub n plus 2 is equal to F sub n plus 1 plus F sub n. Basically, the Fibonacci sequence, each next term is the sum of the previous two terms. And then we have to give you not just the first term, but actually the first two terms. So the 0th term of the Fibonacci sequence is 0, and the first term of the Fibonacci sequence is 1. And then you can say, if you let n equal 0, the 0 plus 2 second term is equal to the 0 plus 1 first term plus the 0th term, which is just 1 plus 0, which is 1. And then you can keep, it gets to be tedious to keep writing this out, right? You could write like for n equals 1, F3 is equal to F2 plus F1, which is just going to be 1 plus 1, which is 2. But then you can just kind of do like, I'm just going to keep adding the two numbers together. So the next one's going to be 1 plus 2, which is 3, and then 2 plus 3, which is 5, and 3 plus 5 is 8, and so on and so on and so on. It's a very interesting pattern. There actually is, sorry about that. If it ever looks too blurry, let me know. There actually is a really kind of interesting explicit formula for the Fibonacci sequence, which we won't talk about here, but it is related to the golden ratio, which is kind of bizarre. But anyway, Fibonacci sequence, kind of cool. So yes, it goes on 1, 1, 2, 3, 5, 8, 13, et cetera, et cetera, et cetera. I think you could all observe here that this sequence, does it converge or does it diverge? Definitely diverges, right? Just getting larger and larger and larger. So certainly the Fibonacci sequence diverges. And if I wanted to be a little bit more explicit about how it's diverging, you could say it diverges to infinity, because the limit as n goes to infinity of the nth term of the Fibonacci sequence is in fact infinity, right? It just keeps getting larger and larger and larger. They're never getting smaller. So there's a famous recursive sequence, probably the most famous recursive sequence. Not that it's all about the fame, but you know, we'll see things like that. Let's look at a less famous recursive sequence, but still an interesting example. Let's say we have a recursive sequence that's defined as a sub n plus 1 is equal to the square root of 2 times a sub n. Or as I like to think of it, my next term is equal to the square root of 2 times the current term. I always think of the sub n plus 1 as the next term, and the a sub n as the current term. Although I think previously I said previous term, but that's probably not as good. All right, and oh, of course I have to give you the starting term. So we're going to say that a sub 1 is equal to 3. So let's find a few terms first, and then we will talk about finding the limit of this. So a sub 2 is going to be the square root of 2 times a sub 1, which is the square root of 2 times 3, which is just the square root of 6, which we could get a decimal approximation is about 2.45. All right. Let's look at the next one. Here things start to get kind of gross. So a sub 3 is the square root of 2 times a sub 2, which is the square root of 2 times the square root of 6. Which is about 2.21. And what I start thinking about when I start writing these terms down is, okay, well, it looks like things are getting smaller. And this kind of makes sense because right, I plugged in 3, I got a number smaller than 3 back, and now I'm plugging in a number smaller than 3, and I'm getting a number smaller than that back. And so it seems like if I keep doing this, I'm going to keep getting smaller and smaller numbers, but how small? Like all the way down to 0? Could it even be negative? It couldn't be negative here. And here's how I know it can't be negative. If I plug in something positive and multiply it by 2, it's still positive, and the square root of that is definitely positive. So I really like to kind of think about what are my terms doing, especially in recursive sequences. We'll write one more. The next term is the square root of 2 times a3, which is the square root of 2 times all of this. Square root of 2 times the square root of 6, which is approximately 2.10. And I'll just tell you without writing it out, the a sub 5 is approximately 2.05. So it kind of looks like we're getting closer and closer to 2. That seems like a reasonable, plausible guess. In fact, I would point out that if you keep plugging in numbers larger than 2, like 2.05, 2 times a number bigger than 2 is a little bit bigger than 4. And if you take the square root of a number a little bit bigger than 4, the result's going to be a little bit bigger than 2. So every time you're plugging in something a little bit bigger than 2, you're still going to get something back that's a little bit bigger than 2. This also makes me think that 2 is probably a fixed point. So let's find the fixed points. So as a reminder, to find the fixed points, which we also call equilibria, we're going to just replace each a sub whatever with the capital L, or any letter you like, but L is the common choice. So we're going to take this recursive equation, or difference equation, as some people call it, and we're going to rewrite it as capital L equal to the square root of 2 times L. That's always the process for finding the fixed points. You just take every a sub n plus 1, a sub n plus 2, a sub whatever, place each and every one of them with L, even if there's more than 2 of them. And then we're going to try and solve for L. I'm going to square both sides. I'm not going to divide both sides by L. I'm going to subtract 2L from both sides, and then factor out an L. So in this case, we get 2 possible solutions. We get L equal to 0, and we also get L equal to 2. And both of those are fixed points. If you plug in 0 for a sub n, 2 times 0 is 0, and the square root of 0 is 0. You get 0 back out. If you plug in 2 for a sub n, 2 times 2 is 4, the square root of 4 is 2, you get 2 back out. So that's, again, what makes it a fixed point, is if you plug that value in for your a sub n, your a sub n plus 1 is the same value. Now, looking at the first 5 terms here, which of those fixed points makes sense as the actual limit of this sequence? Obviously 2, right? Things you seem to be getting closer and closer to 2. So we're pretty sure we think that the limit as n approaches infinity of our sequence a sub n is in fact 2. And that's kind of all we can say about this currently. Let's look at another example. Yeah, I like this next example too. Let's say we have another recursive sequence. We'll do 2 more, and then we'll talk about, geometric sequences for a hot minute. Let's say I have a sub n plus 1 equal to 12 divided by 1 plus a sub n, and we're starting with a sub 1 equal to 1. If you're being asked to think about the limit of these recursive sequences, you really do kind of need to write out a few terms, because if we just started by finding the fixed point, like let's do that first, or I should say fixed points, plural. We're going to have L equal to 12 over 1 plus L. I don't like solving equations with the denominator, so I'm going to multiply both sides by 1 plus L and get L times 1 plus L equal to 12. Let's see, L times up. So I'm going to get L squared plus L on the left equal to 12, or subtract 12 and get L squared plus L minus 12 equal to 0. And then hopefully it factors. It does factor as L. Wow, it doesn't factor like that, James. It factors as L plus 4 times L minus 3. So your fixed points are L equal to -4 and L equal to +3. And again, I like to kind of, I like to write things so you can see them, usually. So I would, again, if I plug in 3, 1 plus 3 is 4, 12 over 4 is equal to 3. I get 3 back. If I plug in -4, 1 plus -4 is -3, 12 divided by -3 is -4. So again, just re-emphasizing here that if you plug in a fixed point, you get back that same value. That's what makes it a fixed point. All right. So which of these seems like a plausible limit for our sequence? Well, we have to plug in a few values to get an idea. If I plug in 1, my a sub 2 is going to be 12 over 1 plus 1, which is 6. Here again, I'm going to start thinking about the fact that if I'm plugging, I'm really like to pay attention to the sign. If I plug in a positive number, 1 plus a positive number is still positive, and 12 divided by a positive number is still positive. So I don't think -4 is going to be reachable, at least with a starting place of +1. So I'm pretty sure that -4 is out. It is possible that both fixed points are not the limit, that the limit actually doesn't exist. But usually we don't encounter that. If you've got some fixed points, usually, except in the next example, one of them is your actual limit of your sequence. So here, I'm just going to check 2 more values. My a sub 3 is going to be 12 over 1 plus 6, which is 12 over 7, which is approximately 1.71. And my fourth term is going to be 12 over 1 plus 12 over 7, which is starting to get kind of gnarly. Using a calculator, that's approximately 4.42. So we kind of looks like we're bouncing down below 3 and then back above 3. And then I bet the next one's going to bounce back down below 3 and then back above 3. So we're kind of oscillating back and forth, but we're closing in on +3 as our limit. So, and if we look at the next, sure, I'll just tell you a sub 5 is approximately 2.21. A sub 6 is approximately 3.73. A sub 7 is approximately 2.53. So yeah, every even numbered term is a little bit bigger than 3, but getting closer to 3 by decreasing. And every odd numbered term is a little bit less than 3, but getting larger and larger, again, looking like it's getting closer to 3. So it's a pretty good bet. The limit, as n goes to infinity, of this sequence is in fact 3. And all right, let me give you one more example before we talk about geometric series. So, where'd you go? Example. Oh, you're on the next page. Oh yeah, that one's fun. Cool. So let's look at this example. A sub n plus 1 is equal to 4 over a sub n. So, and we're going to start with a sub 1 equal to 1. And before we start doing anything, let's find the fixed points. So, in fact, why don't you all find the fixed points? So I want you all to solve this equation. L equal to 4 over L. There should be 2 solutions. I'll give you a minute. I encourage you to make this as your first step. All right, close enough to a minute. L times L is L squared. 4 over L times L is just 4. And if L squared equals 4, then L is either going to be +2 or -2. Those are our fixed points. If you plug in 2, you get 2 back. If you plug in -2, you get -2 back. And if we plug in 1, what's the next term of our sequence going to be? Show me any fingers. Thank you, not many. Yes, 4 over 1, just 4. And if you plug in 4, what's the next term of your sequence going to be? Oh no. Oh no. And if you plug in 1, you're gonna get 4. If you plug in 4, you're gonna get 1. If you plug in 1, it's just bouncing back and forth between 1 and 4 forever and ever and ever. And even though there are some fixed points over there, this sequence, at least if you started at 1, doesn't ever get closer to 2 or negative 2. It just keeps bouncing back and forth between 1 and 4. So this sequence, the limit as n goes to infinity of a sub n does not exist. Or you could say a sub n diverges. The only way the sequence could converge is if you started at a fixed point, at 2 or at negative 2. If you start anywhere else, you're just keep bouncing back and forth between 2 different values. In fact, you could start somewhere else. Like if you started to say same example, but now you're going to say that my a sub 1 is equal to 3, then your a sub 2 is going to be 4 divided by 3. Your a sub 3 is going to be 4 divided by 4 divided by 3, which is equal to 4 times 3/4, which is still 3. You're basically just taking the reciprocal each time. You're getting one thing, then the reciprocal, then the other thing, then back and forth, back and forth. So yeah, this one doesn't converge unless you start at a fixed point. Diverges. So just to point out that just because there are fixed points, that's not a guarantee that your recursive sequence will converge to either of them. But most of the time it will, so usually you should be fine. All right, let's look at geometric series here, because we have, so yeah, I want to get to this example, but I really need to talk about geometric series before we can get to that example. I have a word problem coming up, just need some geometric series. So what is a geometric series? In fact, I really should say geometric sequence / series. The difference, not that it's super important in this class, but the difference between a sequence and a series is a sequence is a list of numbers in order. A series is a list of adding up those numbers in order. So like, for example, your sequence, can I spell this again? Your sequence might be something like 1, 1/3, 1/9, 1/3 cubed, 1/3 to the 4th, et cetera, et cetera, et cetera. Whereas your series is the same terms, but you're adding them. So it's 1 plus 1/3 plus 1/9 plus 1/27 plus 1/3 to the 4th, et cetera, et cetera, et cetera. That's the difference between a sequence and a series. The sequence is just the list. The series is you're adding up the terms in that list. Yeah. What makes this geometric?
You divide the next term by the last term. It's going to give you the same value.
Right, exactly. You divide any term by the previous term, it should always give you the same ratio. Another way to say that is from one term to the next term, you should be able to multiply by the same ratio and always get the next term. So here it looks like our ratio is 1/3. 1 times 1/3 is 1/3. 1/3 times 1/3 is 1/9. 1/9 times 1/3 is 1/27. 1/27 times 1/3 is 1/81, and so on and so forth. So here we would say that the ratio is, and we usually use a lowercase r equal to 1/3. And I will point out, or I'll just say that for a geometric, don't want to say that just yet. No, I don't want to say that just yet. We're not quite there. Yeah. Another example could be the geometric series 8 minus 4 plus 2 minus 1 plus 1/2 minus 1/4, et cetera, et cetera, et cetera. And here it looks like every time to get from one term to the next term, we're multiplying by -1/2. So here our ratio is equal to -1/2. Yeah. And typically we kind of like to write these in a specific way. So like this first one, I'm thinking of as 1 times 1/3 to the 0th plus 1 times 1/3 to the 1st plus, I don't really need to write the 1 in front, I did here, plus 1/3 squared plus 1/3 cubed, et cetera, et cetera, et cetera. Same idea here. Here I'm really thinking of this as, I want to write this down here, 8 times 1 plus 8 times -1/2 plus 8 times negative 1/2 squared plus 8 times negative 1/2 cubed. So you can kind of see that each term is just your ratio raised to the next power. That's what's happening here. That's what's happening here. And it's going to make it easier for us to find out what these add up to. That's really why we're writing it like this, so that we can then find the formula for what it adds up to. And I should actually take a quick pause. Has Dr. Diddell talked about geometric series in class? Okay, yeah. So I'll try not to say too much about it, but I'll also try to say enough about it. But let's talk about how we're going to find the formula for the sum of the first n terms. There is a formula for the sum of the first n terms of a geometric series. Often called the nth partial sum. And it's written like this. So we're going to say that Sn is equal to the first term. Well, actually, not. I should be careful here. We're actually going to call this term I just wrote, which I'm really trying hard to not say the first term. We're going to call that the 0th term. So this is the 0th term. And really, the number of the term is referring to like the power that's on the ratio. So it's your 0th term, and then that times your ratio, and then that one times your ratio, and every next term you're just multiplying by your ratio again, so you're just increasing the power of your ratio all the way out to the last term, which is the a times r to the n. So it's kind of weird because, or I should say, the naming isn't great, because technically we're saying this is the nth partial sum, it's the sum of the first n terms, but if you actually look, it's n plus 1 terms, and you've got 0, 1, 2, 3, 4, all the way to the nth term. It's not a big deal, but sometimes people are like, well, wait a minute. So that's what's really happening here. So this is the nth term. Okay, so we want to find out what this adds up to. And there's actually a really kind of convenient formula for this. I suppose I should show you how we get it, because it's kind of cool. So how do we derive the formula for what these add up to? Like, I don't want to write all this out every time. So here's what we typically do. We take this formula, and we're going to multiply the whole thing by r. So I'm going to say, great, r times the nth partial sum is going to be a times r plus a times r squared plus a times r cubed plus a times r to the 4th plus all the way to second to last term is a times r to the n plus a times r to the n plus 1. And now we're going to subtract these two things from each other. And do I want to subtract them in a particular order? Not really, but I'm going to do this one minus that one. So look here. On the left-hand side, Sn minus r times Sn. Cool. On this side here, let's be smart and not write out a billion things. If you subtract this minus all of that, the a times r's are going to cancel. The a times r squareds are going to cancel. The a times r cubes are going to cancel. Everything's going to cancel except for this 0th term here minus this a times r to the n plus 1 over here. I'm happy to say more about that if there are questions about that.
Where did you get that again?
So what I did here was I took this entire equation and I multiplied it all by r. So on the left-hand side, I got r times Sn. On the right-hand side, each of these terms got multiplied by r. So now this is a times r, a times r times r, a times r squared times r, and so on and so on and so on. All the up to the very last term being a times r to the n plus 1. And then if I subtract this minus all of that, on the left-hand side, I get Sn minus r times Sn. On the right-hand side, I get a plus a times r minus a times r, plus a times r squared minus a times r squared, plus a times r cubed minus a times r cubed, all the way to plus a times r to the n minus a times r to the n, and then finally a minus a times r to the n plus 1, because there isn't anything to cancel that one out. And all the terms cancel except for the a and the minus a times r to the n plus 1. And now we're going to do some fancy algebra here. Not really. We're going to factor out an Sn from the left. You have Sn times 1 minus r equal to, I'm going to factor out an a from the right-hand side. A times 1 minus r to the n plus 1. And then we're going to divide both sides by 1 minus r to get that the nth partial sum is equal to A times 1 minus R to the n plus 1 divided by 1 minus R. Kind of neat. I think it's kind of neat. So for example, if I wanted to find the sum for that first example, if I wanted to find, like, say, the fourth partial sum, which was for 1 plus 1/3 plus 1/9 plus 1/27 plus 1/81, instead of adding them all up, which I could do, I could just throw them into this formula and say, okay, well, my A is 1, right? That's my 0th term. My R is 1/3. And so then, and my N is 4. And if I plug those all into this formula, my S4 is going to equal 1 times 1 minus 1/3 to the 4th power over 1 minus 1/3. I know it doesn't look very nice, but it is what it adds up to. We can simplify it, but I don't think we really want to simplify it here. I made a small error, sorry. Yeah, thank you, exactly, right? I said 4, but it should have been 4 plus 1 there. So really this should be 1 times 1 minus 1/3 to the 5th over 1 minus 1/3. And then we could simplify it. This would be kind of gross. On top you have 1 minus 1 over 243 over 1 minus 1/3, which becomes 242 over 243 divided by 2/3, which is 242 over 243 times 3 over 2. That's a 121 over an 81. Which I'll point out, if you add these together, should add up to the same thing. All right. Why do we care? You guys, like, this seems like kind of like you're just messing around. The reason we care is because, well, two reasons really. We can actually talk about what a limit of a geometric series is. Like, we can ask the question, what if you keep adding up terms forever and ever and ever? Well, let's look at an example. In fact, let's look at this example. What if we want to find the limit as n goes to infinity of Sn? In other words, what if we want to find 1 plus 1/3 plus 1/9 plus 1/27, and we just keep going forever and ever and ever and never stop? Well, sometimes you're going to get infinity, right? If you add a bunch of things and they're not getting smaller, it will be infinitely large. That's not the case here. Here, the things are getting smaller, and what's going to happen is we can say, well, I'm going to say that's equal to the limit as n goes to infinity of the formula. Take my formula, my n is 1, my A is 1, good God. My R is 1/3, the power is n plus 1, and then we have 1 minus 1/3 on the bottom. Okay, really important thing to observe here. As n gets really, really big, what is 1/3 to a really big power going to do? Is it going to get big or is it going to get small? It's going to get small because we're multiplying 1/3 by 1/3 by 1/3 by 1/3, and every time you multiply something by something that's less than 1, it gets smaller and smaller and smaller. I should really say something whose absolute value is less than 1. So whether you're multiplying by 1/3 a bunch of times or by negative 1/2 a bunch of times, you're still getting closer and closer to 0. What that means here is if you take the limit of this 1/3 to the n plus 1 is going to go to 0, and you're left with 1 over 2/3, which is 3 over 2. So that geometric series, that sum of an infinite number of terms, is going to add up to 3/2. Or really should say, when you add them all up, it gets closer and closer to 3/2. On the other hand, just to kind of contrast that, if your geometric series was, say, 1 plus 2 plus 4 plus 8, 16, where every term is double the previous term, what's our ratio here? Show me on your fingers. Yeah, it's 2, right? Every time you get to the next term, you're multiplying by 2. And so you can also, I don't think you actually have to do this one, although I'm going to, but you can just look at this and see, not only are the terms themselves going to get infinitely larger, but if you're adding up a bunch of things to get infinitely large, certainly the sum of them is going to get infinitely large. But if you actually throw it into the formula, this formula that you can't see anymore that I'm pointing to. So if we take a look at this, we know that our A is 1 and our R is 2. And if we find Sn equal to A times 1 minus R to the n plus 1 over 1 minus R, that's going to look like, and then we take the limit of it. The limit then goes to infinity of 1 divided by -1 is -1. So you have -1 times 1 minus 2 to the n plus 1. But 2 to a really big number is going to be a really big number, right? Try plugging in 2 to the 1000th to your calculator. It's hugely big. So this is really, really negatively big, but then it's negative times that. So this is going to be positive infinity as expected. So if your ratio is between -1 and 1, then your series will converge. But if your ratio is bigger than or equal to 1, or less than or equal to -1, then the series diverges. Do I have anything else I really want to say about that? No, not really. Other than the example that I've been trying to work my way up to here. So questions about this before we do an example? To me, it always feels kind of funny that we talk about this here because this is like one small slice of what other calculus classes talk about as far as sequences and series go. But it's kind of all we do here. Like we talk about geometric series and then you're done. We're going to move on with calculus and talk about continuity and derivatives and all that jazz. But here's a small piece of series. So let's look at this example. Which example? Yeah, let's do that one. So there's many questions like this that I've seen recently. Here's one example. This is apparently similar to, or maybe exactly, number 35 from section 2.1. Number 30, yeah. So 2.1, 35. Please ask questions along the way. So here's the setup. There are some words. A doctor prescribes a 100 milligram antibiotic to be taken every 8 hours. Which is always challenging. You have to do it like right when you wake up and then midday and then like right before you go to sleep. Just before each pill is taken, 20% of the drug or antibiotic from the previous dose remains in the body. When you're doing these questions, pay special attention to this part of the statement because sometimes they'll talk about how much is left, how much they'll talk about how much is gone. Like if they said instead 70% of the drug has been eliminated from the body, that means there's still 30% left. And we're always kind of focused on how much there is, not how much we've lost. So just pay attention to the words there because sometimes people try to be kind of sneaky. So part A, and there's a few parts here. How much of the drug is in the body just after the second pill is taken? And then also the third. I like to make a table for these kinds of questions. Just like I also like to make a table like for the exponential growth and decay kinds of questions that we'll probably see eventually. So I'm going to make a little table where on the left-hand side I have n for the number of doses. On the right-hand side, I'm going to use Q sub n for the quantity of drug or the amount of drug. So amount after the nth dose. So I take my first pill, and right as I take the first pill, I'm gonna have 100 milligrams of drug in my body, assuming instantaneous absorption, which is probably not a realistic assumption, but hey. Okay, and then 8 hours later, we take the second dose, and here's what's happened. I have 20% of what was there. So I'm going to take and let's actually show the math, not just say the numbers. So I'm going to have 100 times 0.20, and then I'm going to add another 100 milligrams of drug, which is going to equal 120 milligrams. Same thing for the next dose. When I take my third pill, I'm going to have 20% of how much was there before. So 20% of 120 milligrams plus another 100 milligrams. Which if we simplify this, well, I actually think simplifying this is not super useful here, although I'm going to do it anyway. 0.2 times 120 is 24. So you're going to get 124. But I think this is kind of obscuring what's really important here, is kind of the formula thing that's happening. So here, you're getting 100 plus 100 times 0.20. Here, I would actually like to write this as this whole formula kind of written out. So here's what I mean. It's going to be 0.20 times the previous thing that we put in for 120, which is 100 times 0.20 plus 100. And then plus another 100. And if I kind of FOIL or expand this out, here's what I've got. I've got 0.2 times 0.2 times 100, or 0.2 squared times 100, plus 0.2 times 100, plus 100. Or written in a more suggestive way, I have 100 factored out times 1 plus 0.2 plus 0.2 squared. Oh, it's looking kind of geometric with a ratio of 0.2. Interesting. So that's the answer to the first question anyway, right? We just want to know how much after the second dose, how much after the third dose. Let's ask the next question. Not that question. Sorry, there you go. Sorry, I'm looking at the wrong one. Yeah, so usually for questions like this, they want you to then write a difference equation. AKA a recursive sequence for Q sub n plus 1 in terms of Q sub n. So what they're asking you to do is take some amount here and say, well, what do you need to do to that amount to get to the next amount? Well, it looks like, here's what I did. I took my previous amount, I multiplied it by 0.20, and I added 100. I did that here as well, right? I took my previous amount, multiplied it by 0.20, and then added 100. So it looks like if Q sub 3 is equal to the previous amount, Q sub 2, times 0.20 plus 100, I can just replace the 3 with n plus 1 and the 2 with n. So I can say, oh, that's going to be Q sub n plus 1 equals Q sub n times 0.20 plus 100. And that's kind of it. Is this super helpful? Maybe. Is it answering the question asked me to answer? Certainly. Could we find a fixed point here? Probably. Let's do it. So again, find a fixed point, you take all your whatever sub n's and replace them with capital L's. So we're gonna have capital L equal to capital L times 0.2 plus 100. We're gonna subtract the L times 0.2 from both sides and get 0.8 times L equal to 100. And then we're gonna multiply both sides or divide both sides with 0.8 and get L equal to 100 divided by 0.8, which is like 125. I think it's 125. Let's see. Yeah, it's 125. Right, because you're dividing by 4/5, which is like multiplying by 5/4, which is 125. Okay. So wow, it looks like we got really close after the third dose here, right? Like I'm kind of surprised. I'm like, that seems like a mistake. Now that, oh, I'm looking at the wrong amount. Sorry, I keep looking. Sorry, there's two. Let me cover that paper up. I'm really blowing it here. Oh, seems fine. Okay. Yeah. I'm personally surprised because I'm like, oh, after the third dose, we got to 124. Oh, but then we're gonna have less and then more, right? You guys look like you have questions. How did I get 0.8? Good question. How did I get 0.8? So from this step to this step, here's what I did. I subtracted L times 0.2 from both sides. What's 1 of L minus 0.2 of L? 0.8 of L. Right, there's a 1 there that I didn't write, but 1 times something minus 0.2 times the same something is 0.8 of that same something. So that's how we got the 0.8. And then the math I was doing in my head here that I didn't write down, this is really, 0.8 is really 4/5. And so then you have 100 times 5/4. And 100 divided by 4 is 25, and 25 times 5 is 125. That's how we're getting that number. So later on, when we ask the final question, like what we think the limit of this is going to be, it's probably going to be 125 milligrams. And if you kept doing this process forever, which you wouldn't because you don't take antibiotics forever, probably, maybe, I mean, nothing forever, right? Because eventually we die. But certainly, if you did continue this process forever, you would get closer and closer to having just a constant amount of 125 milligrams of this antibiotic in your body. Let's answer the more interesting question is, what's the explicit formula for Q sub n as a function of n? Well, I don't personally find it helpful to know the difference formula for that. Like, there's probably a slick way of taking this difference formula and finding out what the explicit formula is. I'm not good at that. I'm going to look back at the stuff I did before and say, okay, well, I know that if I'm looking for Q3, it's going to be 100 times 1 plus 0.2 plus 0.2 squared. And I can do the same sort of thing for Qn, right? So I know that I'm thinking Q sub n is equal to, sorry, you can't see that. Let me bring this down here so you can see that. So it's going to be 100 times 1 plus 0.2 plus 0.2 squared plus all the way to, when I did Q3, I ended at 0.2 squared. So when I do Q sub n, I'm going to end at 0.2 to the n minus 1. That's what I would expect. And does that seem reasonable, or would you like me to say more about that? I feel like people are like, say more about that. Okay, let me say more. So back up here for a second. If I was going to find after the 4th dose, look what's going to happen. So I'm going to take my 3rd dose and I'm going to multiply it by 20%. So my Q4 is going to equal 0.2 times my 3rd dose, and I'm going to add on 100. But if I multiply all of this by 0.2, I'm going to distribute the 0.2 in. So look what's going to happen. I'm going to get Q4 equal to 0.2 times 100. I don't love the 100 right there, but fine. Times 1 plus 0.2 plus 0.2 squared plus another 100. But now look, the 0.2 multiplied by each of these things here is going to give me 100 times 0.2 to the first plus 0.2 squared plus 0.2 cubed. And then right here I have 100 times 1. If I put this all together, hey, look, I've got 100 times 1 plus 0.2 to the first plus 0.2 squared plus 0.2 cubed. So every time I go to the next quantity, I'm just going to add on another power of 0.2 inside the brackets here. And that highest power is 1 less than the number of doses. That's what I'm focusing in on there. So I can see, oh, great. If Q4 is 100 times 1 plus 0.2 plus until I get to 0.2 cubed, then I know that if I'm going to the nth dose, sorry, paper's everywhere. The nth dose is going to be 100 times 1 plus 0.2 plus 0.2 squared all the way up to 0.2 to the 1 less power than the number of doses here. Cool. And then we recognize this geometric. So we can use our geometric formula and say, okay, well, my A value is 100. That's my first term. My R is 0.2. This is going to add up to A times 1 minus R to this power plus 1. I'm not going to say m plus 1. It's the last power you had plus 1. So it's going to be to the n, all divided by 1 minus 0.2. Which I can make look a little bit nicer by remembering that 1 minus 0.2 is 0.8 and 100 divided by 0.8 is 125. So the nice simplified version of this formula is that Qn is equal to 125 times 1 minus 0.2 to the nth power. And then if you took the limit of this as n goes to infinity, the 0.2 to the nth power would get smaller and smaller and smaller. And this would go to 125 as n goes to infinity. Unsurprisingly, because we already knew that 125 was a fixed point. So we're not at all surprised that the limit of this looks like it's 125. It is 125. All right. Questions about this example? I know it's kind of a lot of pieces moving there, but this is not atypical. The minus 1 here.
Like from the equation, like from the one to the left.
So this equation here. Oh, sure. So I'll remind you, and let me just write it down again. The formula that I'm using here is that if you have some A times 1 plus R squared plus all the way to R to the N, that's going to equal A times 1 minus R to the N plus 1 over 1 minus R. So the idea here is that whatever this highest power is here, this power is going to be 1 more than it. So here, the highest power was n minus 1, and n minus 1 plus 1 gives you exactly the n. Other questions about this? All right. As much as I would love to say more, we got other things to talk about. So last class, we tried to say all we could about limits as quickly as we could because I wanted to show you all the limit things before your exam on yesterday. But now let's kind of go back and be a little bit more explicit about the different types of, I'm specifically thinking of zero over zero limits that you're going to see. We've already kind of talked about the infinity over infinity ones, I think enough. So let's focus a little bit more of our time on the 0 over 0 ones. And in my opinion, the 0 over 0 types fall into 4 subcategories. 2 subcategories, and one of the subcategories has 3 subcategories. So 0 over 0 types, it's either going to be a do some algebra kind of type. And the algebra things we can do are either factor and cancel. Typically, you're always factoring and canceling at the end of the process, even if you've done one of the other 2 things I'm about to mention here first. The other 2 things you might see are multiply by a conjugate, if you see square roots, or get a common denominator if you see fractions and fractions. And then the other 0 over 0 type is sine x over x. Those are the primary types of 0 over 0 limits you're going to see. Well, let's look at some examples. The limit x approaches 2 of x cubed minus 8 or x squared minus 4. We should always check before you start factoring to your heart's content. Plug in the 2 just to make sure that it is in fact a 0 over 0. You don't actually have to write it down, but you need to check that you do get 0 over 0 before you start doing any too much work. Because sometimes someone's gonna slip something in where it's not 0 over 0, and then you're gonna do all this factoring, and it'll be for no valid reason. Yeah,
If there's like a number over 0, does that just go to infinity then?
we'll talk about that. But yes, that's next on the list. So here, if I plug in 2, I get 8 minus 8 over 4 minus 4, which is 0 over 0. So we factor. The denominator is easy enough to factor. It factors as x minus 2 times x plus 2. The numerator is a little bit more complicated. You're definitely going to get to x minus 2, but the rest of it is, So there's a way to factor a difference of cubes. And there's also a way to factor a sum of cubes. So if you have a cubed minus b cubed, it factors as a minus b times a squared plus a times b plus b squared. And just to add it in, if you have a cubed plus b cubed, it factors as a plus b times a squared minus ab plus b squared. Some of you may have heard the acronym SOAP. For this, it stands for the sign is the same, the sign is the opposite, and the last sign is always positive. Whether it's a cubed minus b cubed or a cubed plus b cubed. Factor and cancel. So x cubed minus 2 cubed, right? That's what this is. X cubed minus 2 cubed is going to factor as x minus 2 times x squared. Let's see. So same, opposite. So plus 2x, and then always positive, plus 2 squared. And then we can cancel the x minus 2's, or divide x minus 2 by x minus 2 is equals to 1. And then we have the limit as x approaches 2 of x squared plus 2x plus 4 over x plus 2. And now we can just substitute in 2 for all the x's and get 2 squared plus 2 times 2 plus 4 over 2 plus 2, which is going to be 4 plus 4 plus 4, which is 12, over 4, which is 3. On the other hand, just to be kind of a little bit silly about it, but if we said what's the limit as x approaches 3 over x cubed minus 8 over x squared minus 4, you shouldn't do any of that work. You should just plug in 3 and say, oh, it's going to be 3 cubed minus 8 over 3 squared minus 4, which is not 0 over 0. It's 27 minus 8 over 9 minus 4, which is 19 over 5. So if you can just substitute in whatever x is approaching and get a real number, that's good enough. That's you, with rare exceptions, that is totally the right thing to do. All right. Let's look at some more examples, like the limit as x approaches 2 of 5 minus the square root of 8x plus 9 over x minus 2. Sure. So I'm going to check. I know we have problems either way. If I plug in 2, certainly the denominator is going to be 0. But if the numerator is not 0 and the denominator is 0, then we have a whole other thing we're going to do. But here, if we plug in 2 to the top, 8 times 2 is 16. 16 plus 9 is 25. Square root of 25 is 5, and 5 minus 5 is 0. So it is, in fact, a 0 over 0 type. So we're going to do some algebra. In this case, the algebra being multiplied by the conjugate of the thing with the radical. So we're going to take this limit as x approaches 2 of 5 minus the square root of 8x plus 9 over x minus 2, and we're going to multiply by 5 plus the square root of 8x plus 9. And of course, we can't just multiply the top by whatever we want. We have to multiply the top and bottom by the same thing that we're multiplying by 1, so we're not changing the value of this limit. Whenever you're applying this idea, you always want to actually multiply out the conjugates and not actually multiply out the not conjugates. So the denominator here, I'm just gonna leave alone. I'm gonna leave the denominator as x minus 2 times 5 plus the square root of 8 plus 9. So the limit is x approaches 2 of x minus 2 times 5 plus the square root of 8x plus 9. Why do we multiply by the conjugates? Because it gets rid of the radical. So if we multiply at the top, I really don't want to show this intermediate step. What I would really encourage you all to skip to is just saying, oh, I know that when I multiply conjugates together, solve the denominator here. But when I multiply the conjugates together, I get the first thing squared minus the second thing squared. What happened, which I encourage you not to show the work I'm about to write down because no one needs you to show it. But the work that happened that we didn't show was you have 5 times 5. You have 5 times the square root of 8x plus 9. You have negative square root of 8x plus 9 times 5. So negative 5 square root of 8x plus 9. And finally, you have minus square root of 8x plus 9 times the positive square root of 8x plus 9, which is negative square root of 8x plus 9 squared. And then the middle terms end up subtracting to 0. But you don't need to show that step, so don't show that step. Unless you want to, then you totally can. So then we simplify and watch out. The denominator is still just x minus 2 times 5 plus the square root of 8x plus 9. There's really absolutely zero benefit to multiplying at the bottom because we are hoping that that x minus 2 cancels. You should leave it factored out if you want it to cancel. In the numerator, I have 25 minus 8x plus 9. Minus parentheses 8x plus 9. It's minus all of that. Be extra careful because if we didn't have those parentheses, we'd end up with 25 minus 8x plus 9, which is 34 minus 8x, and x minus 2 isn't going to factor out of that. So we have to be extra careful here. When you have minus some stuff, you have to have minus all the stuff. Simplifying a bit, the limit is x approaches 2. 25 minus 9 is 16. So we have 16 minus 8x, all over x minus 2 times the other stuff. And then what can I factor out from the top? Right. So I'm exactly going to have the limit as x approaches 2 of negative 8 times. You can either write negative 2 plus x, or you can write x minus 2. They're the same thing. That's a 5 plus the square root of 8x plus 9. And then the negative 2 plus x divided by the x minus 2, those are the same, so they divide to 1. And here you have the limit as x approaches 2 of negative 8 over 5 plus the square root of 8x plus 9. And then when you plug in the 2, you get negative 8 over 5 plus the square root of 25. So you get negative 8 over 10, which is negative 4/5. Cool. Some more. All right, where's this? Kind of one. So the third kind of algebra thing that we often run into is getting a common denominator if you have like fractions and fractions. So another example would be something like the limit as x approaches 5 of, I have to think there for a second. Brain, sorry. I had a good example in my head, now it went away. X minus 5 on the bottom, and I wanted something fun on top. Sorry, my brain just stopped working. It's okay. I know, I'm just trying to think of something that's like not just like the obvious, like I could just do 1 over 5 minus 1 over x. That feels very kind of not exciting. Oh well, doesn't have to be exciting. Okay, so if you plug in 5, you're going to get 1/5 minus 1/5 over 5 minus 5, which is still a 0 over 0. So we have to do something. And there's actually kind of two ways to deal with specifically this kind of example. Either way, you're going to need the fact that the common denominator of these two fractions is 5x. One way to deal with this is to say, great, I'm just going to get a common denominator. I'm going to multiply 1/5 by x over x. I'm going to multiply 1 over x by 5 over 5. I'm going to simplify this as the limit as x goes to 5 of x over 5x minus 5 over 5x, all divided by x minus 5. And then I'm going to write that as the limit as x approaches 5 of x minus 5 over 5x. Instead of dividing by x minus 5, I should multiply by what? One over x minus 5. Because really, although it's not written down there, the bottom is really x minus 5 over 1. So we're going to multiply by the reciprocal and say, oh yeah, this is equal to the limit as x approaches 5 of x minus 5 over 5x times 1 over, oops. I feel like I flipped something here. Did I? No, am I just crazy? Yeah, I made this one. Yeah. Bummer, I didn't do the thing I was hoping to do. Oh, well, it's fine. And then the x minus 5 divided by x minus 5 is 1. So you can say that's the limit as x approaches 5 of 1 over 5x, which is going to be 1 over 25. Let's look at one more example of this, just because I want to show you one other thing that happens, but I don't want to do the same example. Let's look at something very similar, like the limit as x approaches 6 of, sure, 1/3 minus 2 over x all over 6 minus x. Yeah, that's better. Okay, so one way to do this kind of problem is to do like we just did it. Multiply the 1/3 by x over x, the 2 over x by 3 over 3, and get a common denominator. Another way to do it, though, is to see that we know the common denominator would be 3 times x. And so we're just going to multiply the top of this fraction by 3x and the bottom by 3x. Let's see what happens. So I multiply the 3x by the top, I'm going to distribute. I'm going to get the limit as x approaches 6 of 1/3 times 3x minus 2 over x times 3x, all over 6 minus x times 3x. But the point of doing this was that when you multiply the 1/3 by 3x, the 3's cancel, and you just get x. And when you multiply 2 over x by 3x, the x's cancel, and you just get 2 times 3. This ends up becoming the limit as x approaches 6 of x minus 6 over 6 minus x times 3x. And here, so we could have also gotten here by doing it the other way. What I want to point out here that's a little bit different than the previous example is in the previous example, you had x minus 5 divided by x minus 5 is 1. Here we have x minus 6 divided by 6 minus x, which you could do more factoring for, or you can multiply, well, we can multiply the top and bottom by -1, or you could just know that if you subtract something in the opposite order, it's the negative of what it was. What's 5 minus 2? Everybody. What's 5 minus 2? 3. What's 2 minus 5? -3. What's 3 divided by -3? Right? -1, right? And it doesn't matter what numbers you pick, as long as they're not the same. Any two numbers subtracted divided by the opposite subtraction, they'll always be negatives of each other, and they'll always divide to -1. So x minus 6 divided by 6 minus x is going to be -1, as long as x isn't equal to 6. And you know what? It isn't, because x is approaching 6, but not equal to 6. So it's totally fine to say, oh yeah, that's equal to the limit as x approaches 6 of -1 over 3x, and then that's -1 over 18. Or you could do it the other way and multiply. You could say it's the limit as x approaches 6 of -1 times x minus 6 over -1 times 6 minus x times 3x, and then actually simplify the bottom part and say it's the limit as x approaches 6 of -1 times x minus 6. But then -1 distributed to 6 minus x is really positive x minus 6. And then you can cancel those, and you're still left with -1 over 18. Either way is fine. Whatever is comfortable is what you should do. I'm just trying to show you that you can get away with showing less work if you remember a few things. All right. Those are the algebraic ways. Let's talk about not 0 divided by 0. let's say we have the following limit. As x approaches sure 3 of 5x over 2x minus 6. So I don't love this question. Because if you plug in 3, you get 15 over 0. To deal with limits like this specifically, you really have to look at the one-sided limits. So we're going to actually look at what happens as we approach 3 from either side. The limit as x approaches 3 from the right. And the limit as x approaches 3 from the left. And in either case, I still recommend factoring if you can. So I would first factor out a 2 from the denominator and say I have 2 times x minus 3. Now here's what I want you to ask yourself. If you plug in a number just a little bit bigger than 3 and subtract 3, is that going to be a little bit negative or a little bit positive? A little bit positive. So here's what I want you to write. On the top, you're going to have 5 times 3, which is 15. On the bottom, you're going to have 2 times a slightly positive number, which we like to write as a 0 with a positive superscript. Then you have a positive number divided by a positive number, which is positive. But when you divide by a really, really, really small number, what happens to your fraction? It gets really big. So here's the thing about dividing. It actually is the inverse of what you have. So in fact, let me just point out that function, 1 over x, is called the inverse function because it takes your input and gives you the inverse of that input. So if your input is large, like 1,000 or 1,000,000, 1 over 1,000 or 1 over 1,000,000 is small. So it inverts what you have. A big thing inverted becomes small. A small thing inverted becomes big. If you plug in a small number like 1/1000th, f of 1/1000th is 1 over 1/1000th, which is 1,000. This is always the nature of fractions. If you're divided by something big, it's going to give you something small. If you're divided by something small, close to 0, it's going to give you something big. So here we have a constant number divided by a very, very small number. So the result's going to be big. Positively big or negatively big? Oh, we know it's positive because it's a positive divided by a positive. And then from the other side of 3, if you pick a number that's a little bit less than 3 and you subtract 3, is the bottom going to be slightly positive or slightly negative? Slightly negative. So then this is going to be equal to still 15 on top, right? You're not going to plug in 2.9 on top and get 14.5. You're going to plug in 3 on top and get 15. And the bottom, you're saying, well, I'm plugging really close to 3. It's going to be slightly negative. Oh my God. Oh, it's terrible. The worst thing I've ever written. Negative, not -1, just negative. And then a positive number divided by a negative number is negative, negatively large. Question?
If it goes with 15 over 0, is it possible that it will have limit that exists?
No, definitely not. These limits do not exist. But again, we're talking about how they don't exist in a very specific way. We're saying, I know this limit does not exist. And also, from the right-hand side, it's getting infinitely large. And from the left-hand side, it's getting negatively infinitely large. But yes, it is also correct to say that both of these limits do not exist.
So, if we come across this on a test, we can't stop at 15 over 0.
You should not stop at 15 over 0. You should say more.
Prove that.
Right. Now, here's what I'll say about this one specifically. If you graph this, you'd have a vertical asymptote at +3. And from the right-hand side, the graph would be shooting up to infinity. And from the left-hand side, the graph would be shooting down to negative infinity. That's what this kind of limit actually tells you about the graphical behavior. Is as you approach 3 from the right, it's going up, 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 up. As you approach 3 from the left, it's going down, 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 down. But since the right-hand side and the left-hand side aren't going towards the same infinity, If someone asked about the double-sided limit, you would still say it doesn't exist, and nothing else can be said. So I'll point out here that the limit as x approaches 3 of 5x over 2x minus 6 does not exist in any way. On the other hand, if someone were to ask us about, say, the limit as x approaches -2 of 5x over, sure. Yeah, do I want that? Yeah, over x plus 2 squared. Well, if I plug in -2 here, I'm going to get not 0 divided by 0. That's how, by the way, this is, I typically call these not 0 over zeros. So when you have a not 0 over 0, you only have 3 choices for your answer. Your answer could be infinity. Your answer could be negative infinity. Or if it's a double-sided limit where the infinities don't match up, it could be does not exist. Those are the only things that can happen if you have not 0 divided by 0. Let's see what this one's going to do. And to be perfectly honest, most of these questions get asked as one-sided limits to start off with. Like if I was writing a test here, I'd really write it as like, find the limit as x approaches -2 from the left, and then find the limit as x approaches -2 from the right. And then does the double-sided limit exist is not the right word. Does the double-sided limit go to the same infinity on both sides or not? So here, let's look at both sides. The limit as x approaches -2 from the left of 5x over x plus 2 squared. So again, I'm just plugging in. In the numerator, I'm going to get 5 times -2, which is -10. In the denominator, a number that is less than -2. -2.1. You don't actually plug that in, but you think about it. You're like, okay, it's more left than -2, so it's -2.1. -2.1 plus 2 is slightly positive or slightly negative. Right. So it's a slightly negative number, but then it's getting squared. So the denominator is certainly positive and the numerator is certainly negative. So the overall result is negative. On the other side, as x approaches -2 from the, oh my gosh, as x approaches -2, holy shit, oh my gosh. Sorry, x approaches -2 from the right-hand side of the same thing. Be careful here, it can be confusing what you're plugging in. You're plugging in -2. So on top, you're getting -10 still. In the denominator, you're plugging in a number that's a little bit to the right of -2, which is like -1.9. If it helps you, I highly recommend drawing a little number line. There's -2. Oh yeah, over here it's like -1.9. Over here it's like -2.1. Just so you know what's happening on the left and the right of your number. It's always a little more challenging for negative numbers. And then we plug, and then we say the denominator is a slightly positive number, but it's squared. Well, it doesn't actually matter because it was positive already, but you have a negative over a positive, so the whole thing's going to be negative again. So in this case, although all these limits don't exist, I would say that the limit as x approaches -2 of the 5x over x plus 2 squared, the double-sided limit, is also negative infinity. And all this means graphically is that at -2, at x equals -2, we have a vertical asymptote where both sides go down to negative infinity. Like that. That's what's happening graphically. Oh, time. Never enough time. So what I think I will do for Thursday, since we didn't get to talk about continuity at all today, is certainly, if I really can find the time, record something, but if I can't find the time, find a video where I talk about continuity and ask you all to watch that. Yeah, because we're definitely not going to talk about continuity in the last 5 minutes of class here. So instead, with our last 5 minutes of class, let's talk about the other type of 0 over 0 limit, the sine x over x type of limits. So I know we talked about one of those last time. I'll remind you that if you have the limit as x goes to 0 of sine of x over x, that limit is equal to 1. And then, I had some examples I wanted to make sure yeah, sure. Oh, yeah. So as long as the insides go to 0 and the insides of the sine function in the denominator are exactly the same, then that limit's going to be 1. So for example, I can say the limit as x approaches 3 of sine of x squared minus 9 over x squared minus 9. It doesn't matter that things look a little funky. I've got sine of something over the same exact thing, and that thing is getting closer and closer to 0 as x is closer and closer to 3. So I say definitely that's going to be equal to 1. And there's not really any work to be shown here. Unfortunately, kind of. Like I wish there was work to show, but there really isn't. Yeah. But then things get a little bit more complicated. Like if I want to find the limit as x approaches 0 of sine of 8x over 2x. We've almost met all the criteria, but not quite. We have sine of something over a slightly different something, but those somethings still are both going to 0, right? In fact, I should have been following my own advice. For each of these, I should have checked before I did anything to make sure it was a 0 over 0 type. A reminder that sine of 0 is equal to 0. So certainly each of these is. I get sine of 0 over 0, which is 0 over 0. I get sine of 9 minus 9 is 0 over 9 minus 9 is 0. And I get sine of 8 times 0 is 0, 2 times 0 is 0. They're all 0 over 0 types, so we can or should be doing stuff here. So here, there's a couple ways to do this. Here's what I know I want. I want to have sine of 8x over 8x. So some people do this in various ways. One way you can do this, which isn't the way I usually do it, I keep grabbing the wrong pen here, is you can say, well, if I want to get 8x on the bottom, I'm going to multiply by 4 over 4. So I write this as the limit as x goes to 0 of 4 over 4 times sine of 8x over 2x. Leave this 4 out in front, but multiply the 4 in the bottom times 2x, and you get the limit as x goes to 0 of 4 times sine of 8x over 8x. And then you can even bring the 4 out in front. Say it's 4 times the limit as x goes to 0 of sine of 8x over 8x, which is just 4 times 1, which is 4. It's easy when the numbers multiply nicely. It's less easy when you have something like the limit as x approaches 0 of sine of 5x over 7x. There isn't a nice integer number to multiply by 7 to get to 5. There's a fractional number. You could certainly multiply the top and bottom by 5/7, but I don't like to do that because it just doesn't feel natural. To me, what feels natural is to do this. Although I will admit it feels natural just because I've done it for so long. But I like to do what I called last time, and I think I did say this last time, which was the wish method. I think, right? Where you say, well, I have the things I started with. I'm just going to break them up into multiple fractions. And then beneath the sign of whatever, I wish I had whatever. So beneath sine of 5x, I wish I had 5x. Well, wishes come true. There it is. But then if I divide by 5x, I also have to multiply by 5x. And then these x's over here always get to cancel. And so I'm left with the limit as x approaches 0 of sine of 5x divided by 5x. Let's pull that 5/7 out in front. And that's going to be 5/7 times 1, which is 5/7. Let me give you one more example because they can be trickier than this. Let's say we had something like the limit as x approaches 0 of sine squared of 3x over 4x squared. So you might have noticed for these last couple ones that you have kind of this pattern of like, oh, I had sine of 8x over 2x, and my answer was 8 over 2. I had sine of 5x over 7x, and my answer was 5 over 7. And if you have sine of a multiple of x over a different multiple of x, that will work every time. But if you start squaring things, it's less good. So don't rely on that pattern being true. I'm going to do the same thing I did before, kind of. I'm going to write this out as the limit as x goes to 0 of, I'm going to write 3 fractions. Because I have sine of 3x times another sine of 3x, because that's what being squared means. You have it multiplied by itself. And then times something over 4x squared. All right, same question as before. What do I wish I had beneath sine of 3x? But if I have one there, I need one there. What do I wish I had beneath this sine of 3x? Also 3x. And then the x's cancel, right? This x, and this x squared, those all cancel out or divide to 1. So we're left with the limit as x approaches 0 of sine of 3x over 3x times sine of 3x over 3x times 3 over 4, which ends up being a 1 times a 1 times a 9 over 4, which is 9 over 4.